Welcome to Complexity Made Simple. My name is Paul Allen, and the subject of today's newsletter is probably the most important subject I've ever learned in all my Six Sigma work, and it's how to transform your capability statistics. When you have poor capability statistics, what do you do about it? So let's get this as a heading. So we are going to learn to transform poor capability, in particular your poor CPK. Now I'm going to say this video is probably going to go on 30-40 minutes, so if you don't have time to watch it right now, put it aside and watch the whole thing from beginning to end and make some notes. This is the most important thing I've ever learned as an engineer. So let's take a look at this thing. So what do I mean? Which capability problem am I talking about? Well, essentially you're going to have two capability problems. One of them is going to look like this. So you have too much variability. You have results hanging out of both sides of the tolerance. The other capability problem you have will look like this. Sticking with the same tolerances. Going to look like that. Now this one is easy to fix. This one will have a root cause. So this one is relatively easy. You'll have root cause. In other words, you'll have a single variable. So essentially what can you do here? Well, you can do your 5 whys analysis and your root cause analysis and things like that. Typically fixing this will take 3 days. This is a problem with the mean, it's a problem with the center. It's what I would say is a problem with the noise. If you haven't seen my other videos on signal and noise, go take a look at it. So this is a problem with signal. Moving the signal is dead easy. Normally you grab a dial on the front of the machine and you can make the process move around. 3 days to fix that, maybe even 3 minutes if it's just moving a dial. This is what I want to talk about, because this is hard yards. This is changing the noise. Now this is going to take you, so the technique I'm about to show you, most important that you know this. I'm afraid it's going to take you 3 months. This is not a problem with signal, this is a problem with noise. This is a process which is chaotic. Lots of variables are moving around. This is hard yards to fix, and you need a completely different technique to this. So I'm going to show you how to fix this. Just to show you, by the way, the other thing I would definitely do before I draw these pictures, I would also draw a run chart. So if I draw a run chart of the chaos, so what does a process in chaos look like? It's going to look like this. So your process is jumping around. Sometimes it knocks over the top tolerance, sometimes it knocks over the bottom tolerance. So this is a process in chaos. What would this thing look like? Well, completely different. So again, always draw the run chart. First thing you should always do, draw the run chart. This is going to look like this. And then when you fix it, it's going to look like that. So you're going to be sitting up here on top tolerance. 3 minutes, 3 months. Draw these graphs, draw these pictures. Most important that you do this before you do anything else. So, now I normally teach this technique with one of these. So I give groups of people in my classes a catapult to play with, and I just ask them to do a very simple thing. So here you can see me in a video just introducing the exercise, and all I basically do is I give them a catapult and I just ask them to fire the catapult multiple times using an identical setting. So normally I ask them to go back to 177 degrees. I ask them all to fire the catapult. So every operator gets to fire the catapult, just like would happen in a normal process where operators change every day and teams change and shifts change. So I just say to them, fire the catapult 25 times from an identical setting. And that's the way we set the exercise up. And I set the two groups running exactly like you can see in this video with me conducting a lecture. Now the two groups that you can see in that lecture room, they came back having fired the catapult from an identical setting with ranges, this width here, with ranges of 34 inches and 43 inches, yes, for the same setting. Now I've set them a challenge. I want them to land in a target which is just 4 inches wide on the last day of my course. And currently they can land the ball in a target which is this big. Okay, now you need to do the same thing. So job number one is you go to your process. You do 30 pieces. And you do 30 pieces hands off. Okay, you do 30 pieces hands off. No adjustments in those 30 pieces, just 30 repetitions. Because what we want to see is how much chaos is in your process. How much chaos is built up because of lack of maintenance, poor material that you're purchasing, variability in the material, etc., etc. Settings don't move if you leave them alone. So they won't be causing this if you leave your settings alone. Okay, so we need to see what the nature of the chaos is. And once we have 30 pieces hands off and we've plotted a run chart, a histogram, and finally a Cpk diagram, so we can see the nature of our problem. Once we've plotted those three, now we are ready to tackle the problem ahead. Now I'm going to show you what to do next. Okay, now that we've taken some data and we've discovered that our problem is about too much variability, we're going over the top tolerance and below the bottom tolerance without even touching the machine. Okay, the technique you're going to need, and as I mentioned earlier, this is going to take 3 months to do this. The technique you're going to use is known as process flow, cause and effect. Now just something to say, Six Sigma has a reputation for being about huge amounts of maths and statistics and analysis and stuff like this. These are just 2 of the 7 quality tools. This is the most important thing you can do. Six Sigma is not about all that mathematics. It's about understanding and being able to transform your capability to a level that your business needs. Whether that's 6 Sigma, 5 Sigma, 4 Sigma, it's up to you to decide. But I need to give you the tools to be able to do whatever you want to your process capability, and this is one of those tools. So the catapult groups, what am I going to teach them to do? Well, the first thing I'm going to ask them to do is to do a flow diagram of the process of firing a catapult. That's job number 1. Now, the idea of the flow diagram, it is a guide to help you because your processes are highly complicated. If you just sit in a room and ask a bunch of experts, what do you think is the cause of this? they will all just go, I know what it is, and they'll just name one or two things. Now we're going to have a much more highly defined solution than that. Your problem is much more complicated than just one thing going wrong, and we need a technique to help. So the first thing we're going to do is a nice detailed flow diagram of the process of firing the catapult. Okay, I've quickly drawn a flow diagram of the process of firing the catapult. Now this is what the groups are asked to do. Okay, so this is a guide to what we're going to do next, because what we've got to find is a high definition problem definition. High definition. Just finding one thing wrong with your process is a low definition way of doing it. It rarely ever works. What we need is a high definition problem approach, and this is what we're going to do. We are going to visit every box on this flow diagram, and we're going to ask the question, what were the variables at that step that contributed to my 43-inch range? Okay, what are the variables? Because think about it, it's physics. If you do the same thing, you get the same result. It's simply the laws of physics. That's what Six Sigma brings to you. All this nonsense about whether it's the 1.5 sigma shift and all sorts of things. Guys, it's physics. Just use physics to your advantage. And here's how we're going to do it. If you do the same thing, you get the same result. If you get the same result, you transform your process capability. So let's do this, look. We're going to go at the setup phase. Okay, what were the variables that we set the process up that contributed to our 43-inch range? Well, let's think about it at setup. What were the sort of things? Well, under machine, the stability. Very good pen. Let's use another one. The stability of the catapult, because they just placed it on the carpet and every time they fired it, the thing bounced around. What else? We can do this under the measurement, I think. The stability of the tape measure, because it was just placed on the, so this is just in this box. So we're just in this box. We're asking ourselves a question. When we did the setup, what variables did we place into the process? Now this is really important. I'm asking for difference, I'm asking for movement. I'm not asking for problems. So we're not saying, what's a problem? What problem were we having? No. What was changing? What was moving? What's variable? Yeah, so the stability of the catapult is variable. The stability of the tape is variable. We had 5 operators. I mean, you could call that in real life, of course, 5 shifts. Yes, we've got 5 shifts working on this particular process. So we had operators. What else? What else at the setup phase? Anything? Maybe the position of the people. So I'm going to put that under method. So position of operators. Because sometimes when you're doing the return process and you're doing the spotting process, if you're standing in the wrong place, you get the wrong answer, so you create variability. So there's 4 variables just in the first box. Okay, then we keep going. Okay, loading the ball. Now, what was the variation in loading the ball? Now in this particular, I haven't got a ball with me, but in this particular piece of equipment, if they force the ball into the cup, the ball will stick in the cup. And of course, it just doesn't want to fire, or it fires much shorter than before. Whereas if they just lightly drop it in, it will just fire obviously much better. So at the load phase, under methods, what variables have we got? Well, we've got the load force, putting pressure on the ball. And here's a great example. Nobody's having a problem loading the ball. No one's having a problem loading the ball. They just put the ball in the cup. But if you all do it different, some people force it in, some people just drop it in, we get a different result. That's just physics playing through the process. Okay, so what else have we got here? Now, at loading the balls actually aren't very round. So of course, depending on which way round you put the ball, that might have an effect on how far the ball fires. So let's have a look. Under material, I'm going to specify ball roundness. Now you'll notice I'm being very specific. So under material, I haven't just said the ball varies. It doesn't mean anything. If you talk to your operators, they will say, the material varies. What do you expect us to do? That doesn't mean anything. If they tell you that the thickness is changing, the width is changing, the hardness is changing, the density is changing, whatever it happens to be, you can then measure it and figure out what to do about it. So the more specific you do this, the more high definition you do this, the better control you'll get under the process and the more you will transform your capability. So what we're going to do now, we're going to go down and say, okay, what was the variables at the pullback? So let's have a look. Maybe the grip method that we use, whether you pinch it or whether you stick your thumb on the top when you pull the arm back. Under methods, when you pull the arm back, the hold time. So how long you hold it down for. One of the problems with these catapults, when you pull the arm down, this pin rotates here. The longer you hold it, the more the pin rotates, and the more it affects the balance in the elastic band. And it creates variability. Hold time. So we've gone setup, what are the variables? Loading the ball, what are the variables? Pulling the arm back, what are the variables? Now we're going to do that all the way down and complete the cause and effect diagram. And this is what you do for your own process. Now what I'm going to find, I'm going to get about 15 variables on this thing in total, approximately. In your processes, you could find between 50 and 100 variables. This is a high definition technique. You are going to find out everything about your process. I'm now going to complete the cause and effect diagram. Okay, I've been through every step of the flow diagram. I've identified variables at each stage. The flow diagram was a guide to make sure that you get a high definition analysis of every variable in your process. Here are all the variables completed. Now this is what the groups do in the exercise. What I then ask them to do is very simple. I just ask them to make a list of all the variables. By the way, very important, the variable only exists on here once. Yeah, there's only one time it's happening, so we just put it up there once. Pick a heading and put it under a suitable heading. Doesn't matter really which heading it goes under, the key point is that you find them. So I found all my variables. We are going to make a list, and you can see that method here. So we're going to make a list of all the variables, and against each one we are going to come up with a method, a standard, an agreed way of reducing the variability to as small as it can possibly be for that variable. So for example, for the 177 degrees at the back of the catapult here, what do most groups do? They simply find a nice hard stop and they pull it onto a nice hard surface, and they're guaranteed 177. So some of the solutions almost eliminate the variability. So suddenly we've got no variability in the pullback angle. Some of the solutions though, like the load force, all you can do is to come up with a good, specific, standard operating procedure for loading the ball. So it may be something like pull the arm back and then drop the ball in from about 10 millimeters above the cup. Very specific, very controlled, and then we teach that to all 5 operators. By the way, the one variable in the exercise that they can't get rid of is the 5 people. That's because that's what life's like. You have 3 shifts, 4 shifts, 5 shifts, depending on what shift patterns you have in your company. You have lots of people running the same machine. You have to be able to deal with labour churn. Yeah, it's just a way of life. So I'm going to force them to change operators in this exercise, even the second time that they fire it. So what they do is they come up with great methods where it's people related. They come up with engineering solutions where they can, and they take the variability and they reduce the variability to as small as it can possibly be for each one of these. Then they put that into action and they fire again. Now imagine this. You suddenly don't allow variability into your process. If you don't allow variability into your process, guess what happens? You don't get variability out of your process. And what you basically do is you take this capability. When you do this, you control the inputs to your process. When you do this, and what you do is you remove the variability, because that's what's causing the problem, and you stand your capability on end. And you get this when you control the variables. You transform the capability and you make piles of money. Now there's a little example. Here's a group doing this. Look, here's the list of all the variables, and you can see against each one they've come up with a solution, and they've done exactly this. And usually in the second round, so what did we say? We had a range of 43 in the first round. They get a range of between, I would normally say, between 7 and 3 inches in the second round. So a dramatic transformation. Now think about what they're capable of doing now. In the first round, with the 43-inch noise, if I'd have moved this cup to try and understand my machine, could I have ever seen what the cup movement did to the process? No, not in noise of 43 inches. If I moved this elastic position by 1 peg, could I see what that was doing? No. So all the fancy analytical Six Sigma stuff that people think is what Six Sigma's about, it can't happen unless you do this. Unless you can do this and transform your capability, you cannot do any fancy Six Sigma analysis. And this is really what Six Sigma is about. It's about the ability to transform your capability. It takes 3 months to do it. If this is your problem, it's going to take you 3 months. I can't promise that you can do it any quicker than that, but if you do it, you will make pots and pots of money. Process flow, cause and effect, identify variables, fix variables, transform your capability. Okay, so now, having explained the theory, let's take a look at a few case studies. And we're going to start, most of these case studies, by the way, they're not capability in the sense of hitting a tolerance, they're capability in the sense of hitting a target. So they're pass-fail in nature. Now this first case study we're just going to look at, we've just got the process flow diagram. This is my project. This is the first project. This is the first project I ever did following similar training. So I went on a training course. I was exposed to the catapult exercise. I was told to go process flow, cause and effect, find the variables, fix the variables, and see what happens. And here is my cause and effect diagram. Now I have to say at this point, because this is my first project, this is very naive. This is not my best work. I would do a much more detailed cause and effect diagram today. I will show you a little bit more of how much more detailed it might be with a few examples later on. But let me just show you. Now then, couple of things to point out. The blue and the yellow are the variables we decided to try to fix. So one of the key things about this, often you have so many variables that are out of control that don't have proper ways of eliminating the variability. Some of them are too difficult to control, too expensive to control. So you may decide to look at other things. This is what the n's and the c's mean, by the way. The n means that this variable is not under control. The c means that the variable is under control. I don't need to worry about this particular variable in that case. Okay, so that's what the n's and the c's mean. Now I'm going to turn as many n's into c's as I reasonably can. And the blue and the yellow variables were the ones that we decided to concentrate on in this case. Now this is a defect rate, so the graph we are looking for lower the better. And when we went and fixed those 11 variables, this is what happened to the process. So look at the variability. Look at this thing initially. It's wild to start off with. And all we did was we identified input variables. And I simply removed variation from the input of the process. And if you remove variation, what happens? The variation disappears and the process just went to a great performance. And that was all I did. And that was my first project 20 years ago. And at that point, I was convinced Six Sigma is the tool for me. And this is what Six Sigma is about, by the way. It's about transforming process capability. By the way, look how many days it took me. That's the number of shifts we worked. That's 73 days worth of work right there. So what's 73 days? About a month and a half. Yeah, so it takes about 3 months. It takes about 3 months to do this. So I just removed the variability. There's project one. Even for a very naive cause and effect diagram, I would do a much better one today. The process works. The process works. So let me show you examples from my clients. So this is from a cheesecake factory. Now this is an improvement in line efficiency. They've made the cheesecake, and the last thing they do is they pack them in order that they can be stacked in fours on shelves. And they have a problem that they keep having to box off and put the cheesecakes in a fridge in order to keep them fresh until they can get them back through the packing machine. So let's take a look at this. So what they want to do, look, they've just said, look, they want to reduce the variability. That's all the project says. They want to reduce the variability and they want to get a line improvement of 50% in terms of packed right first time. Okay, so that's what they're aiming to do. Now here's the guy doing what he shouldn't be doing. He's packing the product in boxes. He shouldn't be doing that. They should be going in sleeves, going on pallets, shrink wrapped, out to the supermarket. Process flow, cause and effect. Okay, so very straightforward. Again, in the red, these are the variables that they decided to tackle. These are the important variables that they decided to tackle first. But you can see, look, let's have a look what we've got here. Again, this is their first project. So I have to say there are some things that are a little bit too general for me. So this where it says setup procedure, that's too general. It should be broken down into physical settings, the speed of the machine, the height of the guide, the width of the guide, the choice of the pusher arm, whatever the variable is, they should be written down in individual variables. Like this one here, look. So pusher arm design, cleanliness of the belt, they're nice specific variables. But at the end of the day, even with quite a naive cause and effect diagram, they went away, they fixed the variables, and this was what happened to the problem. So here's the problem. And again, look, lots of variability, but as they get the process under control, it just goes to zero. Then what happens? Some senior manager decides to increase the line speed because he thinks he's got the process under control. The minute he does that, chaos kicks back in. But they don't back away from this. They then retake a look at their controls, put some new controls in, and they drive the problem to the floor again. Look at the improvement in the process capability. There we go. Process flow. This is what this is about. Process flow. Cause and effect. This is why it's the most important thing I've ever learned. In 35 years in engineering, you can fix any problem with this technique, and it requires very little technical capability. You just do a process flow, identify the variables, fix the variables, and your process behaves itself. Let's take a look at another one. Okay, this is from the Royal Mint, close to where I live. Again, another client of mine. This particular process is an annealing process, so it's heat treat. So let's have a look. It's an annealing process, and it's got a particularly high reject rate. You'll see from the graph when we get to the end, again, how wild and out of control the process was, and how simple it was to put the problem correct when you use process flow, cause and effect. So here's the process flow, and that put a little bit more detail in it. Again, my view here is I would probably say they should have more detail on the cause and effect. But again, this is their first project, so they're learning how to do this. What you really want to do is each box wants to contain maybe 5 to 10 variables. And if you do that, that's the ideal detail on a flow diagram. And it's to help you to remember all these variables. Don't forget, there could be hundreds of them. You have to have the ability to come up with, it's helping you to come up with a high definition process understanding. This is high definition process understanding, and that's why it works. This is details, high definition. Let's take a look. Then they come up with the cause and effect. And again, look, they identify a group. They're not going to try and control absolutely everything, but here's what they're going to pick on first. And again, just take that away a second. If you look, the cool down profile. Now in there, I would probably say there is probably 10 variables in that little phrase there, times and temperatures and things like that. I would prefer them to be more specific. So that would be my one criticism of some of these. They're really not down at the variable level, but actually these are the first projects and they all work brilliantly. So they went away, and most of what this was about was stopping the operator fiddling with the settings. So these are coins being heat treated. Some of the coins are very large. Some of the coins are smaller. Some of the coins have holes in and things like that. So there's all kinds of different product running through his machine. What does he keep doing? He keeps playing with all the settings. Keeps playing with these things, trying to get the process to work for the fact that, oh, these are big coins and there's lots of them today. Oh, these are smaller coins and there's not so many of them. And he just played around with all the settings. And one of the main things they did, they agreed some standard settings, just physical controls, physical standard operating procedures. They adhered to them, and this is what happens to the performance of the process. Look at this. You've got wild variability. Now, if you think about this this was a tolerance, the capability we talked about earlier. You see, it's wild variability. You haven't got process capability. In this case, though, of course, this is just the better graph, because this is the acceptance rate. So they wanted to be above 85%. That's where they thought they could be. They wanted to be above 85%. But look at this thing. It's sitting up here at 95%. Far better than they ever imagined. And all they did was simply
remove variation using process flow, cause and effect, remove variation from the inputs to the process, and this works brilliantly. So I've been a little bit critical of one or two of the cause and effect diagrams. It's been a little bit too general. So let me show you a cause and effect diagram that I did that's much more detailed, and it shows you you are literally getting hundreds of variables almost in the process. So this is a cause and effect diagram that I did. It's a few years old, but the variables are much more specific. So you can see, especially down here, look, when we talk about setting, look, we've got compact height, form height, punch height, form punch angle, setting blocks, the restrictor, the blank dimension. They're very specific. This one here, look, too general. Even I fall into this trap now and again. Level of setup. We need it like this, look. Weight, speed, belt tension. It's very specific. And when it's very specific, what have you got? You have high definition. High definition process understanding. And what I can tell you is the world-class companies, that's what they do. They have high definition process understanding. Another way to describe it is they are detailed conscious. So this is, and I don't know how many variables are on here, but you can see we're beginning to get probably up to 80, 90 variables. I've easily done 130 in some of my projects that I've done. When you are at this level of detail, then you will get lots and lots of variables. But unless you come up with a solution, unless you come up with a control for these things, and you can see some of them aren't difficult. They're just individual settings, dimensions in your process, in your tooling, on your machinery. They're actually very easy individually to control. There's just a lot of them. Process flow. So I can't recommend this highly enough. It is the tool that I use in every project. Process flow. Cause and effect. It identifies variables, most important. That's what we're looking for. It identifies variables. And if you control variables, you will transform your process capability.
And just one last point to make about this technique. This technique feeds directly from your FMEA processes when you do new product introduction. This is the exact same technique that the FMEA is trying to get you to do. What does it ask you to do? It asks you to put a flow diagram, the process step on the left hand side of the form. It asks you to identify the failure mode. What's a failure mode? It's a variable that keeps moving. It's an input that keeps moving. And then it asks you to say, what's the effect of that failure mode? What's it going to do to the output of your process? And what you're supposed to do when you create a control plan is to create controls for the variables in the FMEA. So if you use the FMEA properly, you'll never need this and your capability will always be brilliant. But if you've implemented a poor process, or the process is deteriorated to this point and you need to pick it back up and make it work, this is what you're going to use. Process flow, cause and effect. But FMEA is doing the same thing. Your ISO 9000 audits are doing the same thing. What are they doing? They're making sure you've identified the variables, you have rules and you follow them. They're all doing the same thing. They're all trying to get you to make money, providing you understand it's about variables on the input side of the process. If you do that, they all do the same thing, and every one of those techniques makes money. And this is what Six Sigma and process control is all about, making pots of money.